Hello everybody, welcome back. In this video, we are going to be talking about estimating derivatives, and we're going to compare the estimate with the exact. Okay, so let's get started. And we're going to use a simple function here. We're going to use y equals x cubed as our example. And what we're going to do is we're just going to do a couple things. First, we are going to estimate the derivative of this function at x equal 4. Okay? And then we're going to compare with exact. Okay, and we just started doing this recently. Compare. There's a P in there. Anyway, we just started doing this recently, and so you may not be fully okay with the idea that the derivative is slope, but hopefully this video will help and show you that the derivative truly is slope at one point. Okay? So first we're going to estimate the slope. Again, the derivative is the slope. Okay, so to start our estimation, before we start our estimation, we're going to plot this thing. Just a rough sketch, nothing fancy, nothing exact. X cubed looks something like this. If you cube a positive number, it's positive and it grows pretty quickly. And then it has this origin symmetry. It's supposed to be identical. It's not the best graph in the world, but you get the idea. Okay, and just to get an idea of what's going on, let's say this is the x value that we're talking about. Let's say that this is x equal 4. Okay. Now, what we can do to estimate is we can literally calculate slope close to this. Okay, so what I'm going to do is I want to pick a point to the left of x equal 4. I want to pick a point to the right of x equal 4, and I want to find the slope between these 2 points. Okay, and let's see, if I do that, I'll get some, oh, whoa, not what I meant to do, not what I meant to do. Let me try it like this. There we go, like that. If we find the slope between these 2 points, we'll be getting the slope of this little sort of pinkish segment here. And as you can see, this is actually really, really close visually. Without doing any math at all, we see that if we pick a point to the left and to the right of 4, that's actually going to be really close to our, and again, not what I meant to do. That's going to be really close to our slope at x equal 4. You see how these are almost exactly parallel? Okay, that's what I'm talking about. So, pick a point to the left, pick a point to the right, calculate the slope. You're going to get something really close to the actual derivative. Okay? So, that's the idea. Now, let's do it. Okay? Oh, no. Oh, no.
Mr. Phelps with a very special morning announcement. We just learned that our own Mr. Christopher Todd has been chosen to be the Assistant High School Principal of the Year for Osceola County. And so he just received a really nice award here in the main office, and just wanted to let everybody on campus know that Mr. Todd has been chosen as the Assistant Principal of the Year for Osceola County High School. And we are very, very proud of Mr. Todd. So when you see him, tell him congratulations, and we are all so very proud of our Tiger.
All right, sorry about the interruption, everybody. Let's see, is my mic level okay? Mic level, mic level, mic level, mic level. Okay. All right. Okay, so let's actually do this now. So we're going to pick a point. We're going to pick like x equal 3 and x equal 5. Okay, x equal 3 is to the left of x equal 4. X equal 5 is to the right. So that's exactly what I was saying. One to the left, one to the right. And let's actually do the slope, right? So slope is y2 minus y1 over x2 minus x1. Let's get familiar with these symbols. We can also write this as delta y over delta x. Okay. So, what's y1 and y2? Well, let's say x1 is 3 and x2 is 5. Then y1 is f of x1, which, our function here is x cubed. So y1 is just going to be 3 cubed, which is going to be 27, right? 3 times 3 is 9, 9 times 3 is 27. y2, 5 cubed. 5 times 5 is 25. 25 times 5 is 125. So there's y2, y1, there's x2, x1. We have everything we need to calculate slope. So let's do it. M equals y2 minus y1. I've already written that down. 125 minus 27 over x2 minus x1. 5 minus 3. Okay. All right. So 125 minus 27. 98 over 5 minus 3. Well, that's 2. We get the number 49 here. So 49 is going to be the slope of the yellow segment here. Okay. Let's see if we can estimate closer. Let's estimate closer. So like I said in a previous video, we can make delta x and delta y as small as we want. Let's make delta x really, really small. Okay. So instead of picking 3 and 5, let's pick something closer. Let's pick, let's say, 3.9. And for x2, for the right value, let's do 4.1. Okay? And, I will definitely need a calculator for this one. No question. So we're going to take 3.9 and we're going to cube it. Okay. So 3.9. And there's no cube, so we can just times 3.9 times 3.9. Okay. So we get that y1, which is, again, 3.9 cubed. 3.9 cubed we found was exactly 59.319. Let's cube 4.1 now. Okay. 4.1 times 4.1 times 4.1. And we get 68.921. Okay, so y2 is 4.1 cubed, and of course I can't remember anything. 68.921. And once again, we have everything we need to calculate the slope. Let's see how close our 49 was to this. So it's going to be y2 minus y1. 68.921 minus 59.319 over x2 minus x1. So 4.1 minus 3.9. And look at what's happening, right? In this first calculation that we did up here, delta x was 2. In this calculation, delta x is 0.2. So you see what's happening here. Delta x is getting smaller. I'm just going to go ahead and subtract these numbers so I don't make a mistake. 68. Oh boy, 68.921 minus 59.319. And if we do that, that is definitely not correct. Let's try that again. 68.921 minus 59.319. If we subtract those, there we go. That looks more reasonable. 9.602. Over, and then this is just 0.2. So if we take that result and divide by 0.2, we get 48.01. Okay, so based on the first estimate, you would have thought that the slope was 49. Based on the second estimate, 48.01. And here, in the second estimate, delta x was a lot smaller. Okay? Notice delta x is not infinitesimal. Delta x is macroscopic, meaning that it's finite and it's defined. It's a real number. 0.2 is a real number. And that's the gap between x1 and x2. And here it's 10 times smaller than it was here. So this number should be more accurate than this one for the exact. Let's do one more estimation. So let's go crazy here. Let's say x1 is 3.99999, and let's say that x2 is 4.000001. All right. I think you'll maybe see what's going on here. I could keep adding 9s to this x1 as long as I want. Then I'll get closer and closer and closer to the exact value. Likewise, I can keep adding 0s before I get to this 1. And then when I subtract the 2, I'm going to get a number that's really, really small. Delta x is going to be teeny, teeny, tiny. Okay? And I don't want to make any mistakes, so I'm going to rely on my trusty calculator here. I want to calculate delta x first. Okay? 4 point, and then I have 1, 2, 3, 4, 5 zeros, and then a 1, minus 3 point, and then 1, 2, 3, 4, 5 nines. And if I calculate that, I get delta x right there is how many zeros? 1, 2, 3, 4 zeros. And then 1, 1. Okay, so there's delta x. Notice again, delta x is getting close to 0, but not quite. So this should be more accurate than the other two estimates. Okay, so then y1 is going to be f of x1, which is going to be 3.99999 cubed. Okay, so let's do it. 1, 2, 3, 4, 5 times 1, 2, 3, 4, 5 times. There we go. We do this and we get 60. Okay, all right. We get 63.99952 00012. Carrying this out exactly is what I'm doing. Y2, f of x2, which is 4.000001 cubed. 1, 2, 3, 4, 5 times 1, 2, 3, 4, 5. Okay, and we get 64.0000 48, a bunch of zeros, 1, 2, 3, 4 zeros, 1, 2. Okay, excellent. So there we go. We have everything we need. Let's go ahead and calculate delta y. Oops, delta y. If I subtract these two, so I'm taking the 64 point all that minus 63 point all that. So minus 63.9995200000012. Okay, and we get this number in scientific notation. We get 5.279988. I'll carry it out that far. Times 10 to the power negative 4. Which means we're going to move the decimal place 4 places to the left. So 1 and then 0, 0, 0. So 0.00052799988. That's the number we get. And delta x is there. Now, if I've done this correctly, and I really hope I did, this slope, which is just delta y over delta x, which we've calculated everything, over delta x, 0.1234111. So I'm going to take this number and I want to divide this number by 0.000011. And hopefully the result is nice and pretty. Look at that. Look at that. 47.99989. Okay, so look, we started out. Our worst estimate gave us a result 49, then 48.01, then 47.99989. Based on these estimates, what do we think the exact derivative is going to be? Based on these estimates, okay, you know what? Let me change my color. Based on these estimates, okay, based on these estimates, if I can spell estimates, what will the exact value of the derivative, which we can write this way, we can write it this way, we can write it this way. What will the exact value of this be? Okay, without actually doing the calculation, it looks like it's going to be 48. Okay, now let's do the calculation. Okay, let's see. Yeah, f of x is x cubed. The derivative is the limit as h approaches 0, which is the same as delta x. F of x plus h minus f of x over h. Okay, and let's do it, right? So f of x is x cubed. F of x plus h, it just plug in x plus h everywhere. It's x plus h whole thing cubed, which is like x plus h times x plus h times x plus h. I want to do this kind of quickly. The first two, if we multiply the first two out, we're going to get x cubed plus 2xh plus h. I said x cubed. X squared plus 2xh plus h squared. And then we're going to multiply that by another factor of x plus h. Okay? So, just distribute everything. So x cubed, x squared times x is x cubed. Okay? Get a little cluttered here. I'm trying to go this way. There we go. Okay. So let's do the distributive property. That's x cubed. X squared times h plus x squared h. 2, and then we're doing the 2. 2xh times x. That's going to be 2x squared h. And then 2xh times h is going to be plus 2xh squared. Okay, moving on. H squared times x plus xh squared plus h to the power 3. So that's x. This is f of x plus h. Okay. This is f of x plus h. Okay. Now, for the derivative, we need to calculate this. F of x plus h minus f of x. Okay. So let's do this now. We are ready. F prime is going to be limit h approaches 0. F of x plus h. For some reason, I can't scroll to the right with the mouse. It's annoying. So I'm just going to copy this down. This is f of x plus h. So we get x cubed plus x squared h plus 2x squared h plus 2xh squared plus xh squared plus x cubed. Okay, there is f of x plus h, and now we want to subtract f of x from that, okay? And f of x was already given, that's just x cubed. And we're dividing the whole thing by h. And of course, if we try to plug 0 in, we're going to get division by 0, which is just garbage. It's undefined. So, what cancels, right? Well, look at this. X cubed minus x cubed, done. All these other terms have at least an h involved. Before we worry about canceling, though, I'm just going to do some algebra. So x squared h plus 2x squared h. So that's going to be 3x squared h. 2xh squared plus xh squared, that's plus 3xh squared. And then we have the plus h cubed. All that divided by h. Now we can factor. By greatest common factor, we can factor an h out. Because again, we're trying to get rid of that h in the bottom. 3x squared plus 3xh plus h squared. If I factor the h out of the top by greatest common factor, and then I still have this h down here, and h over h is going to be 1. And then what are we left with? Limit h approaches 0, and then boom, what do we got? We got 3x squared plus 3xh plus h squared. And now look, there's no h in the bottom. So if I plug in an h, by the way, something else, these are polynomials. So these are continuous, okay? So continuous, like this is like the continuous limit theorem, right? The idea that if the function in question is continuous, then you can just plug in the value, the x value that the limit is approaching, and get your result. So h is going to 0. So we get 3x squared plus 3x times 0 plus 0 squared. 3x squared is all that's remaining. Everything else is 0. Okay, 3x squared, great. Now in the very beginning we said we're estimating this thing at x equal 4. And we're going to compare that with the exact. So basically just plug in x equal 4 here. Okay? And we can write it this way. We can write it like f prime at 4. We can also write it this way. dy dx evaluated at x equal 4. And of course we can write it this way as well. df dx evaluated at x equal 4. All these are acceptable. It's going to be 3 times 4 squared. And then let's see, 4 squared, 16. 16 times 3. 16 times 3, what is that? That's 30 plus 18, 48. There we go. Okay, so, I know this video is a little lengthy, but I really wanted to show you that, just by using the regular formula for slope, and by considering x values really close to the one in question, in this case x equal 4 is the one in question. If we pick numbers really close, in other words one to the left, one to the right, we can obtain a very accurate estimate of the first derivative. 48.01 is pretty good. 47.99989 is also pretty good. Right? But notice that in the estimates here, delta x is finite. This is a real number. 0.000011 is a real number. Just like 0.2 is a real number. So, for a derivative, if delta x is finite, if delta x is a real number, then your derivative is going to be a little bit off. Notice here the derivative is off. The exact value is 48, but because this is not infinitesimal, we're not going to get the exact result. Down here, this is the result that we get truly when delta x approaches 0. Okay, so there we go.